Hi, I'm Matthew Mance. I'm the project manager and water resource engineer for United Engineers. So I'm here to present to you our project for Crown Point Business Park. So my team consists of an environmental engineer, Morgan, a structural engineer, Addie, and a transportation engineer, Andrew. So for the project overview for Crown Point, we're developing a 40,000 square foot building on a 2.76 acre parcel. And we're developing the infrastructure to support that in terms of the stormwater management and the gravity wastewater collection system. And then also supporting traffic infrastructure, including a roadway that goes through the site and redesign of an intersection nearby. So I'm going to pass it off to my structures engineer, Addie.
Thank you. Good morning, everyone. My name is Addison Januszewski, and I will be going over the structural portion of the project today. So, for the structural portion, it consists of a 40,000 square foot, two-story mixed-use building located at 1106 Maryville Road in Crown Point, Indiana. The first floor is designed for a restaurant space, while the second floor is designed for residential apartment units. The structure is placed on the southeast portion of the parcel to allow for efficient truck access, as well as avoid the designated wetlands and floodplains in the area. So for the structural layout, it consists of a concrete slab on grade for the first floor, a composite floor system for the second floor, as well as a metal roof deck. So steel framing was selected for this project because it allows for longer spans and smaller members while also being extremely cost effective. So for the design codes and loads, everything applicable was applied. The International Building Code, as well as ASCE 7-22 and the ASC Steel Construction Manual. The environmental loads were obtained from the ASCE hazard tool, which included a wind speed of 107 miles per hour, a ground snow load of 50 psf, with a roof snow load of 31.5 psf. The seismic design category is indicated as B, which indicates relatively low seismic risk. The live loads applied were 100 psf for the restaurant floor, 40 psf for the residential apartment units, as well as 20 psf for the metal roof deck, which allows for maintenance. So for the gravity model, it was done in RISA floor to determine different beams, girders, and column sizes. All bending, shear, and moments were checked and verified through RISA floor, as well as through hand calculations. So for the second floor system, it is a composite floor system consisting of a composite metal decking as well as a concrete slab that's about 2.5 inches thick. It is supported by steel beams and girders to support the dead load from that floor. This was also checked and verified through hand calculations. The composite system also allows for an improved system while maintaining relatively a lower dead weight compared to a bigger concrete slab, which allows for lighter steel members. So for the roof system, it is a metal deck that is supported by steel beams and girders as well. The beams have been spaced at 5 foot on center instead of 3.57 so that we can reduce the number of members. The steel beams and girders support the 31.5 psf snow load that's applied to control the deflection of that panel. So for the lateral system, it was modeled in RISA 3D to evaluate against those wind and seismic loads. Again, the wind load is 107 miles per hour with the seismic design category of B. W8 by 10 bracing was selected because we have W8 columns, which allows for easier connections and also improves the constructability, and field work will be a lot easier. It also controls drift as well as providing stability. So for the connection details, we have typical beam to girders, girder to column, as well as typical tension member connections. These were done based off of the largest shear and axial forces to determine the number of bolts required. These were also checked and verified using hand calculations. So for the structural cost estimate, it includes all steel primary members, including the steel beams, columns, and girders, as well as the concrete slab on grade for that first floor, the composite metal deck and topping, as well as the metal roof deck. So it comes out to approximately $813,000. So in conclusion, the steel system meets all ASC requirements as well as all of the applicable loads. It also is within deflection and serviceability limits, and the gravity and lateral analysis has been checked and verified, as well as deflection. It is an efficient and constructible design with an approximate cost of $813,000. I will now pass it off to our transportation engineer.
Thank you, Abby. My name is Andrew Webb. I am the transportation engineer for United Engineers, and I will be talking to you about the transportation part of the Crown Point development. So the first step in the transportation part of this project was to split the site into 19 different parcels, and then select a parcel in the southeast part of the business park to develop. And then next, I developed a main road running through the site, connecting Merrillville Road on the west to Indiana Avenue on the east. So this is a close-up of the western intersection with Merrillville Road. So this road will be 60 feet wide, total right-of-way width. It will have a 27-foot wide paved section, and then at each end it will have a median near the intersection just to improve safety at that intersection. So the cross-section of this road follows the Crown Point standards for a local road. So it will have 2 lanes, each 13.5 feet wide. It will have a 2-foot curb and gutter section on each side, an 8.5-foot green space, and then a 5-foot sidewalk. So the vertical profile for this road is fairly flat. There's a 5-foot elevation difference between the highest and lowest points. The high points occur at the ends of the road at the intersections, and then we have 2 low points at an elevation of 692 feet. So the next part of this project was redeveloping the intersection of Indiana Avenue and Summit Street. This intersection is currently a 4-way signalized intersection operating at level of service C. With all the additional traffic that the business park is expected to generate, improvements will have to be made to this intersection to maintain an acceptable level of service. So this is the alternative that we came up with. This alternative will maintain the level of service C when the site is fully developed. We are adding right turn lanes to 3 approaches, and then we are adding a second through lane to the northbound approach. Additionally, we will be adding crosswalks to all 4 sides of the intersection to allow pedestrians to better access the business park. Additionally, we will be modernizing the signals to add flashing yellow arrows, as this is the new Crown Point standard. This is a zoomed out view of the intersection. Note that north is to the right here, just to fit it on the screen better. So as you can see, heading northbound to the right, the 2 through lanes, the left lane will become a left turn lane into the new road. And then also for this intersection, during construction, it is expected that we will maintain the intersection open to traffic for the majority of the time. However, short-term closures may be necessary. So we have developed a detour route shown here for Indiana Avenue, which follows Monitor Street, Merrillville Road, and then Center Ross Road. And similarly, we have a detour for Summit Street, also following Merrillville Road, Center Ross Road, and then this detour also makes use of Millennium Drive. And lastly, for this project, we developed a parking lot for our building. So the Crown Point zoning ordinance told us that we need 139 parking spaces for this building. About 100 of these are for the restaurant, and then 35 are for the apartments. Additionally, we need a bike rack that can accommodate 10 bicycles, as well as a truck loading area, which will be on the east side of the building. And then finally, I developed a cost estimate for all of the transportation aspects of this project using the 2024 INDOT unit price summary table. So this total cost came out to about $3.1 million. Approximately half of this is for the intersection improvement, and then around $800,000 is for the new road. Parking lot is around $412,000, and then street lighting for the new road, the parking lot, and the intersection comes out to around $460,000. And with that, I will turn it over to our environmental engineer.
Thank you. Hi, I'm Morgan Purser. I'm the environmental engineer for United Engineers. I was tasked with designing a gravity wastewater collection system. So to start off, I just want to go over the overview of the collection system that I have designed and presented on in the past. So this purple line right here, that is or throughout the whole thing, that is the pipeline routing. This follows the right-of-way per the Crown Point standards with a dedicated easement to accommodate for the southern parcels right here, as well as connection to the existing sewer system on Indiana Ave through a lift station and force main, which I will talk more about those in a moment. Each one of these S's with the circles are where my manholes will be located. These manholes are located every change in direction on a straight line that is above 400 feet. They will be located in between 300 and 400 feet on that pipe. Excuse me, the pipe will be 8 inches in diameter. It will as well be PVC piping except for the force main, which will be ductile iron. I will talk more about that. As well as this pipe right here in the middle, it will be ductile iron because we are going underneath the road. So now I want to talk about my lift station design. So to start, I found the lift station pump that I needed. So to do that, I found the horsepower needed, which was 3.44 horsepower. From there, I used the pump curves to find, with a 60% efficiency, to find that I needed an S4S series pump. From there, I used the Myers brand to find this specific pump, which you can see on the screen. It is 5 horsepower with 620 gallons per minute max, which is above our max of 440 gallons per minute. As well as the pump will be submersible and a duplex pump. So there will be 2 pumps next to each other. One will go on for 5 minutes and then turn off. The other one will go on for 5 minutes to ensure that there is no overheating or overworking of these pumps. So then, once I had the pipe, I was able to do the lift station wet well dimensions. So I used the pump dimensions, which you can see on screen. So the pump height is this height right here, the A, which is 2 feet. So that gave our well depth a depth of 10 feet because the pipe comes in at around 5 feet. So that pump is below that. And then we added an extra 20 inches of freeboard to accommodate for the standards, which gave the depth again of 10 feet. And then so next I needed to find the well diameter. I found that to be 9 feet. The width that I used was the longer width, this one right here, which is about 1.5 feet. And then with 2 pumps, you need 3 feet in between them. So once I had that length, I was able to determine that we needed 18 inches around the pumps to ensure that maintenance is able to be done on these pumps. And with that, I found the well diameter to be 9 feet. And so now I want to talk about my force main design. So the force main goes from the lift station into the existing sewer system, which is on Indiana Avenue. It was calculated to be a 4-inch diameter pipe, as well as it will be 184 feet in length from that lift station to the existing pipe. I apologize if it doesn't show up very well on the screen, but this green line is the existing sewer system on Indiana Ave. As well as we will be using ductile iron, as I mentioned, because we do go underneath the road of Indiana Ave, and we just want to ensure that no damage occurs to the pipe. So now my cost estimate. So my cost estimate consists of the cost for the pump, for the pipe, the trenching and backfill, the manhole, and then the lift station cost. So the total cost that was calculated using RS means was $769,000, and then I needed to add a 20% contingency due to any damage or waste that could occur to the materials used. And that came out to be a total cost of $923,000 for the total cost of the environmental section. And I'll pass it off to the water resources.
Hello. For my design requirements for the water resources section of the design, I needed to reduce the total maximum runoff of the site to be less than 0.2 cubic feet per second for each acre of the land that we were using. And with a total of 10.2 cubic feet per second for the entire site was the maximum outflow at any given time. And then for the actual parcel, my design requirements were to reduce the total suspended solids by 80%, the total metal load by 60%, and then also infiltrate 1 inch of water from impervious areas from the parcel. So the required water quality volume was 6,430 cubic feet, which is representative of the water quality volume or the infiltration of 1 inch per every square foot of, or for every 1 inch of runoff for all of the impervious area. And then my final design had 7,110 cubic feet. So I met that requirement using the BMPs. The ones I used were rain gardens, infiltration trench, tree boxes, and then also vegetation swales, and then also a filter strip. So for the total suspended solids, the majority of the site went through different EMP chains. The major ones were the infiltration trench, which throughout the site took about 40% of the total water quality volume, using the 2 different EMP chains, depending on which way the water entered the filtration trench. If it started from the swale, or if it came straight into the filter strip, into the infiltration trench, and then run off the site. So it met the requirement of 80 cubic, or 80% for the total suspended solids by hitting total suspended solids for the site. And then for the total metal removal, I use a similar method where I multiply all of the rates of removal for each BMP, which was the same process that was required for the total suspended solids in the Crown Point standards, and then averaged out then multiplied the rates together to find the total amount of the total metals that's removed. So 74.8% of the total metal load was removed, with the majority of the metal in the site being zinc, which made up 78 or 79% of the entire metal load. So that was the highest concentration of metal that needed to be focused on. However, the 3 highest concentrations were zinc, copper, and lead, which were all removed to meet that total. The other metals weren't factored into the calculations because they were so small compared to the main 3. Would have only been around 7% of the rest of the design. So for the detention ponds, they treat the majority of the water on the site. The bigger detention pond is the East Detention Pond, which takes up around 3.7 acres for the entire space that it's not necessarily using, but for the parcel that's around it as well. So that's like the unusable land nearby it, and then it's a similar value for the area or for the North Detention Pond. Even though they're different in size, they take up about the same amount of space because land nearby won't be usable, just based off where it's located at. And then the new aspect of my design is the infiltration trench, which is included in Area 6 of my site, which will treat the area for where the electrical lines and which I would call a no development area for our land, because we would need an easement, and that would require approval from the electrical companies that have already obtained the rights to be there. And then it'll capture the water for Area 6 and then filter it out. So for the total, for the hydrographs for the site, the total outflow comes up to be around 9.26 cubic feet per second. It's a little bit less than that, as they have different highs in their graphs, so it's probably around 9.2 for the detention ponds, and then the infiltration trenches included for the hydrographs. And they used the majority of the detention ponds that they're in. The East Detention Pond is maximized to pretty much be exactly the right amount of volume that is taken in, and the North Detention Pond has a little bit extra room. for water. And then this table includes the area footprints for the east and north detention pond. The actual area that's used is 1.2 acres for the north detention pond and 2.3 for the actual land use. And then, as I said earlier, the total space that would require is higher than that. And then for the cost estimate from a design, the detention ponds take up the majority of the cost, almost $1 million. And then the other detention or other BMPs or best management practices are also shown in there. The filter strip isn't shown because it was negligent in terms of the total cost. It was calculated out, but from rounding to the nearest 1,000, the values would have ended up being the same. And then the cost estimate for the entire site is $6.5 million. Is there any questions?
Okay, Matt, let's start with you.
Okay.
Can you go back to the locations of these detention ponds you showed? Now, I think my first comment will be about they don't have to be rectangular in shape in there, so you could actually make better use of the land. And you mentioned about like under the power lines, like that's an easement
Well,
section you can use.
They can't use up the space, not because they're just rectangular, but because that they have to be offset from certain distances from certain areas. The north detention pond, I guess technically could be a different shape, but they'd be running in with problems with being below the water table if it went too much further higher in the site.
Okay. I think my comment is about you are using a prime location along the road, and my knowledge of that area says that 1 acre of commercial land is close to almost like $350,000 to $400,000, and you're using that for like a detention pond rather than located in maybe a different location, non-accessible to a prime location. So that's something to consider to reduce to make your client happy, practically reduce the cost associated with all of that in here. And the shape can be, if you push it up next to where you said that you have a flood zone or the wetlands, just a little bit offset, and then you will be in a better shape when it comes to that. Just a comment in here. And the other thing I want to ask you the same question. It was hard for me to see the sizes of the members of the structure in there, but did you consider having those, especially if you're using that building as a restaurant and residential, to include or to locate the AC units, for in this example in here, on the top and...
So yes, I actually did include that in the dead loads that were applied through Lisa Floor. I don't remember the exact dead load weight, but it was applied throughout the model.
And did that reflect the difference in the sizes of the joists and the elements?
Yes, it did.
Okay.
Not too large of a difference, but slightly, yes.
Then Morgan, I have to ask you a quick question. How did you pick up the location of the lift station?
I did it based on the low elevations on the site, since it is a oh wait, sorry, I'm not in the camera. Wait, could I have this one? Let me go back real quick. So I didn't include the contour lines because it just makes it look a little bit too busy, but this is one of the low spots on the site. So I chose that so that gravity was like in our favor, even though we do slope down. And then I also thought about the connection into the existing sewer system, because my other locations were up here, but it made the force main length way like a lot longer. So putting it here, it was closer to the existing sewer system, as well as one of the lower points on the site.
Well, based on the shade on the map in here, without the contours, without the topography, you are so close to the wetland. So is there a guidance in the ordinance about how far away from a wetland you have to be for locating a lift station?
I'm not exactly sure if they had like a specific distance. I do know that we are outside of the wetlands by about, I think, 200 feet.
Okay, you are safe.
Maybe a little less, but I think it was around there. I picked this location last semester, so I don't remember the exact distances. I apologize.
Fair enough, thank you.
Andrew, the intersection at Maribel Road and your new road, is that signalized or stop condition, or how is that working?
So this is just a one-way stop control.
Okay, so it's through traffic on Maribel Road.
Yeah.
All right, Addison, I have actually 3 questions for you.
Okay.
When you showed your snow load, there's one called roof snow load and one ground snow load.
Yes.
I don't know which those
So the ground snow load, obviously on the ground, and then the roof snow load is actually calculated based on the actual structure, so whether it's heated or whether it's exposed to drift from other buildings in the area. So that is often calculated based on the actual structure type. And that's what will be applied to the roof.
And maybe you answered my second question, what is drift? You should drift on one of your slides, and I don't know what drift is.
Yeah, so kind of whenever the building moves, so that lateral stability increases the stiffness, so your building isn't like this, right? It's not drifting over a certain amount, or even snow drift as well, from coming from other buildings.
And my last and most important question is, what time is it in Australia right now?
Add 17 hours to right now, and you'll have it.
I had a couple questions. Morgan, I know you said that your pump that you selected has its capacity, its high flow rate meets your needed capacity, but
Yes.
usually those capacities are for the high capacities at no head, right? So you're going to have to pump up before. So does it still, if you look into, does it still meet the capacity that you need when it's pumping that?
It does, yes.
Okay. Okay. Oh, and then Matthew, so I was curious to know, like you said, zinc was the highest metal load. Could you talk about like how you estimated those metal loads?
Oh, yeah, so I used the source called, it was like Clear Sinks or et al. 2020, and it talked about, it was from this table here, it talked about the different removal rates for each BMP, and then I selected all the ones that actually applied to my site, and I put it in this table here. And then I estimated the removal rates. Or wait, no, sorry, excuse me, you asked a different question. Wait, so this same source had a table for the different parking lot total, the loads for the different metals for different types of roads,
Okay.
different things, and I got it from there, and then I kind of like, it had a little graph and kind of estimated the amount for each of the metals that they showed.
Okay, so just all based on typical values for parking lots or
Yeah,
roads or whatever?
from
Okay,
this source.
okay, thanks. One question for Andrew. You said the road right of way was 60 feet, right?
Yes,
But
that's
then-
the total right-of-way width.
Mm-hmm.
So that includes the sidewalk as well as the grass buffer area.
Okay, and then at the intersection, though, it looked like it got wider. So is the right of way wider at the intersection, and
It
how much,
is.
how much wider?
Yeah, so on this cross-section, this is showing the median cross-section where it meets the intersection. So this adds an additional 10 feet, so that would bump it up to 70 feet.
Thanks.
So a question for you, Andrew. So the other intersection, the one that has the entrance to your building, on that one?
This one here?
Yeah, I think, do you have a larger picture of that?
No, I don't. And it's the same as the Maribel Road intersection.
How, can you give me a sense of how far that entrance to your building is from Indiana Avenue?
I don't remember the number off the top of my head, but I did check that in Vistro to see if the queuing distances were long enough, and it does meet the required distances.
Okay. And that's just a stop too? Like,
Yeah.
And for Matthew, so you answered Professor Weiss's question about the different elements like sink and things.
Mhm.
Can you tell me, because I'm not as familiar about that, where did those come from? Like, why is there sink?
From like carway, or not, I don't know why I said carway, it's just like cars, and like when the water like hits it, it'll be like trace metal of whatever that it hits before it goes through the parking lot.
So all those, that list is all from basically the cars and the truck.
I believe so, yeah.
Thank you.
Any other questions?
Andre?
Oh, Andre? Okay, go ahead.
Matthew, for your total metal load that you're moving, for iron, it said -7. So
Oh.
is that actually added?
Yes, it would be adding iron in that instance.
So what's adding the iron?
Oh, I don't know, that's just, I assumed like the piping in there, that would probably be it. If I had to guess.
What BMP was it that was adding
Oh,
iron?
I'm not sure, that was a really big table.
Oh,
The rain garden and the tree boxes would be adding iron.
okay.
Maybe from the tree, I don't know how plants work, maybe it's in there.
Yeah.
Good eye, Andrew.
Yeah, I mean, yeah. Interesting, okay. Any other questions? Great. Thank you, guys.